Find the average rate of change in a given function. Well, before we can talk about average rate of change, let's just first review rate of change. So what is rate of change? Well, rate of change in mathematics describes how an output value changes relative to the change in an input value. So again, I'm going to read that again. The rate of change describes how an output value changes relative to an input value. So let's look at some examples of rates of change, because no doubtly you've heard the phrase rate of change before. And in mathematics, whenever we talk about rate of change, there is one specific word that I need you to think about whenever you hear rate of change. And that word is slope. Because in mathematics, slope is a specific example of rate of change, because slope examines the change in the y values relative to the change in the x values. Again, y values are outputs, x values are inputs. So slope is rate of change is slope. So whenever you hear rate of change, think slope. Whenever you hear slope, think rate of change, and that's going to help you a lot get through calculus. And let's just quickly examine slope. Remember, we know that slope is the change in y over the change in x, which is y2 minus y1 over x sub 2 minus x sub 1. Again, change in the output with respect to the change in the input. Now, next up, we will look at a different example, one that goes with the real world, and that example is velocity. Velocity is also an example of rate of change, because velocity represents the change in distance relative to the change in time. So for example, when we are driving 55 miles an hour in our cars on the highway, the change in distance is 55 miles, the change in time is per hour. And then our last example is acceleration, and acceleration is a little bit more difficult of a concept to understand as far as rates of change, because acceleration is the change in velocity relative to the change in time. And that's where things could get a little bit confusing, because, well, isn't velocity a rate of change? So then acceleration is just the rate of change of the rate of change, and that's exactly right. Acceleration is measuring how fast the rate of change is changing with respect to a specific time. Now we'll talk about all these things, and we'll continue talking about all these things later on throughout the course. But these are just some examples to keep in the back of your head when you hear rate of change, specifically slope. Slope represents rate of change. So now we can move on to average rate of change. What is average rate of change, and how do we actually find it? Well, the average rate of change of an object measures how much a function changes per unit on average over an interval. Now, these words were chosen very carefully, and they are very specific. So let's read it again. The average rate of change of an object measures how much the function changes per unit. So function changes is the output, and then per unit would be the input. So again, still rate of change, but we're looking at how much the rate of change changes over a specific interval. And that is also key here. So the average rate of change takes place over an interval. Eventually, we will learn about instantaneous rate of change, which happens at a particular moment. But for now, average rate of change, think interval. All right, so the average rate of change, well, if we go back to our definition of rate of change, we know that rate of change is going to be the change in output over the change in input. So the average of that will still be the similar concept, the change in output over the change in input, which we've already said is the change in y over the change in x, which we can even go one step further and simplify that down to be the delta y over delta x, because in mathematics, delta, that triangle symbol, represents change. Now, if you're thinking to yourself, wait a second, delta y over delta x, that sounds so familiar. Where have we heard that before? Well, hopefully you've heard it before, maybe an algebra class, a pre-calculus class, but I definitely mentioned it on the previous slide because we said that delta y over delta x is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And we said that this represents the slope of a linear line. That's our traditional slope formula. So, in addition to the average rate of change representing the change in y over the change in x, we can also say that the average rate of change is equal to the slope of a linear line, which is y2 minus y1 over x2 minus x1. Now, if we want to be a little bit more mathematical or a little bit more precise, we could also write our slope formula as being f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1. Because remember, f of x sub 2 is just another way of writing y sub 2, and f of x sub 1 is just another way of writing y sub 1. It's just more specific. Alright, so let's take a look at an example. So here we're told a rocket is launched vertically upwards from the ground with a speed of 96 feet per second. Neglecting air resistance, because this is a math class, the position of the rocket after t seconds is given by the function s of t is equal to negative 16t squared plus 96t. The position function s of t, meaning this guy right here, is measured in feet, with the ground being s sub t equals 0. So basically what this means is that we can assume that the rocket is being launched off the ground, and it's being launched when our function, again, equals 0. And we are being asked to find the average velocity of the rocket between 1 second and 3 seconds. So here we go. Here we have our interval for the average rate of change. We're trying to find the average rate of change over these seconds, from 1 second to 3 seconds. So, right away we can come in here and let's just call 1 second our t sub 1, and our 3 seconds our t sub 2. Alright, so then we can use our average rate of change formula, but more specifically, we're looking for average velocity, remembering that velocity is a specific rate of change. So let's see, average velocity is going to equal f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1. And while that is true, that's not quite the notation we're given here, because we can see that our function is function s, and we can see that our variables are t. So let's just go ahead and let's rewrite our formula so that it is in terms of this particular example, meaning we're going to have s of t sub 2 minus s of t sub 1 all over t sub 2 minus t sub 1. And we've already identified what t sub 2 and t sub 1 are, so we can go ahead and plug these values in. So s sub 3 minus s sub 1 all over 3 minus 1. Alright, and then we can continue simplifying from here, but before we do that, I'm going to show you a trick to easily calculate these function heights on your calculator. Alright, so in the calculator, we are first going to want to go to y equals, and we're going to want to type in our function, which we can see is negative 16x squared plus 96x. Well, technically it's negative 16t squared plus 96t, but we don't have the variable t in our calculator, we only have x. Alright, but again, it's now in our calculator. Next up, we want to hit seconds, and then the window button to go into the table setup. And we want to make sure that our independent variable is changed from the calculator automatically generating the input values to the calculator asking us what those input values should be. So moved over to ask, hit enter, and boom, we're good to go. From there, if you hit second graph, we're going to go into the table, and now we just enter in our two x values. So we're looking for the output when t is 3, so we'll type in 3, and we get 144. And then when we enter in 1, we get 80. And there you go, boom, let the calculator do all the heavy lifting. All right, so thanks to our calculator, we know what s of 3 and s of 1 are, so we can plug those in. So that's going to give us 144 minus 80 all over 3 minus 1, which can simplify down to be 64 over 2. And I just realized that my 80 looks a lot like an 86, so let's just come in and let's rewrite that, because that should be 80. All right, then 64 divided by 2 is 32. And we are almost finished. We have the numerical value for our average velocity, so our average velocity is 32, but it's 32 what? So we need to talk about the units. Now, if you've done a lot of these applications problems before, or are really good at physics, you're probably going to know what the units are. But just in case you don't, here's a trick you can use in math to figure this out. Again, we know that average velocity is going to be the change in output over the change in input. In this particular case, the output is going to be s of t, and the input is going to be t. Well, our problem tells us that our s of t function is measured in feet. So therefore, s of t is going to be feet. And we know that the t is going to be measured in seconds because it's in t seconds. So therefore, we can see that the average velocity is measured in feet per second, which means our average velocity is going to be 32 feet per second. And boom, there we have it. That is the average velocity of our rocket between 1 and 3 seconds. All right, so now this is a graph of that particular function of the rocket. S of t is equal to negative 16t squared plus 96. Now, one thing that I want to mention here is that s of t is the position of the rocket as it relates to the ground. So this blue line, our function here, represents how far off the ground our rocket is at certain times. So again, we found out that after 1 second, our rocket was going to be 80 feet off the ground. And at 3 seconds, our rocket is going to be 144 feet off the ground. A lot of students unfortunately fall into the trap of thinking that the graph of this function is the path that the rocket takes, and it is not. It is just the representation of how far the rocket is off the ground after t seconds. All right, so again, this is our graph of our function, and we did find the average velocity between these 2 points. And remember, I just want to recall that average velocity, we said, is the slope of a linear line. So on this graph, I don't really see a linear line here. I see a curved line. So what did we actually find the slope of? Well, since we were looking for the average velocity and the velocity is over, or sorry, since we're looking for the average velocity and average rate of change is over an interval, we actually ended up finding the slope of the linear line that intersects these 2 points. The linear line that intersects 180 and 340. And the slope of this particular linear line represents the average velocity between t equals 1 and t equals 3. So with that being said, we need to quickly review some geometry right here. And if we go back to geometry, hopefully remember that any straight line joining 2 points on a curve is called a secant line. Again, going back to geometry, if we intersect a curve, or maybe you heard intersects a circle, that at 2 points, any line that intersects a curve or a circle at 2 points is called a secant line. As we can see, this secant line is the exact same line as our average velocity line. So therefore, we can conclude that the average rate of change is equal to the slope of a secant line. And then the notation that we sometimes use to represent slope of a secant line, we know slope is the variable m, and then to identify this as the slope of the secant line, we are going to have the little SEC for secant. And to take this even one step further, we know that slope is going to be f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1, and this is the average rate of change on the interval from x sub 1 to x sub 2. So this is the formula that we're going to be using in this course to represent average rate of change, and we need to make the connections in our head that the average rate of change is the slope of the secant line, it is m subsecant, and it is the slope formula over a specific interval, meaning that in order to find the average rate of change, we are going to need 2 points. Alright, so with this information at hand, let's go ahead and take a look at some examples. Our first example is we want to find the average rate of change of f of x over the given interval. Again, key average rate of change has to be over an interval. And we're given the function f of x is equal to negative 5x cubed minus 4x squared minus 4x minus 2. And the interval we're looking at is negative 1 to 1. Alright, so let's go ahead and let's get to work. So, we can first look at our interval to identify our x sub 1 and our x sub 2 value. Well then from here we can use our average rate of change formula, and I'm going to abbreviate average rate of change to be ARC, because, well, really I'm lazy and I don't want to have to write average rate of change all the time. So ARC is going to be, as we said before, f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1. And now, based on what we were told in the problem, we know that x sub 1 is going to be negative 1, and x sub 2 is going to be positive 1. So we can go ahead and we can plug that into our formula, leaving us with f sub 1 minus f of negative 1 all over 1 minus a negative 1. And then from here we can use that calculator trick again. So we can plug our function into y equals. We can go second graph to get to the table, plug in 1 and negative 1. And we'll find out that f of 1 happens to be negative 15. F of negative 1 is 3. That's all over, well, 1 minus a negative 1 will change into 1 plus 1. And we can continue simplifying this to get negative 18 over 2, which is going to give us a final average rate of change of negative 9. Now, in the previous example, I made a little hoopla about the fact that we need to have units. And it would be nice to have units in these problems, except we're not given any units here. So, when we're not given units, we don't have to worry about them. But when we are given units, you better believe you got to write them down. So here, we're just going to leave the average rate of change at negative 9 because we don't know any more about the problem. All right, next up, we want to find the average rate of change of f of x equals negative x cubed plus 4x squared plus 2x minus 1 between x equals 2 and x equals 5. So same type of problem, is just worded a little bit differently. Instead of being given the interval in interval notation, we are given the interval with specific points, x equals 2 and x equals 5. Oops, whoa, sorry about that, hit the wrong button. Alright, so from here, we can see that x sub 1 is going to be 2, and x sub 2 is going to be 5. So we can start off with our average rate of change formula, which is f of x sub 2 minus f of x sub 1, all over x sub 2 minus x sub 1. Alright, now we know our x sub 2 and x sub 1 values, so we can substitute those into our formula. So we're going to have f of 5 minus f of 2 all over 5 minus 2. And then using our calculator trick again by putting these into the table feature of our calculator, we can figure out that f of 5 is going to be negative 16. Thank you, Mr. Calculator. And f of 2 is going to be 11. And that's going to be all over, let's see, 5 minus 2 is 3. And then we can simplify this down to get negative 27 over 3, which is going to give us a final rate of change of negative 9. And as we can see, there are no units given, so we can stop right there. Now, please don't start to believe that just because the previous answer was -9 and I chose a bad problem with this answer being -9, that the answers are always going to be -9. That just happened to be a coincidence here. All right, then finally, we're going to be doing the same thing, except the wording here is a little bit different, so I just wanted to quickly review that. So here we're not being asked to find the average rate of change explicitly. Here we're being asked to find the slope of the secant line between two values, which, if we remember correctly, the slope of the secant line is the same thing as finding the average rate of change. So sometimes you might come across problems like this, and you need to tell yourself, wait a second, slope of the secant line is the average rate of change, and then we can go ahead and we know what to do. But we are given the interval from -1 to 2, so we can see that x sub 1 is going to be -1, x sub 2 is going to be 2, so we can get to work. So we're looking for the slope of the secant line, which we know is the same as the average rate of change. So we'll be using our same formula, f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1. And we know what x sub 2 and x sub 1 are, so we can substitute those values in, giving us f of 2 minus f of -1 all over 2 minus a -1. Again, using our calculator, let it do the heavy lifting. We know that f of 2 is going to be -6, f of -1 is going to be 9, and that's going to be over 2 plus 1, because remember, minus a negative is positive. And we can simplify this out to get -15 over 3, giving us a slope of the secant line here to be -5. And that is it, ladies and gentlemen. That is the average rate of change using functions.